Alright guys, this should be the second video, and this will have some of the, not as, you always hear that word high yield. Well, in step one, that first video pretty much covered that stuff you're guaranteed to see. This stuff is kind of like the second tier, but for completeness, I think it makes it for a good job. Just, this should make you well prepared for step one, definitely. Even some items step two and stuff like that. So, alright, so here we go. It says placebo versus new drug X, blah, 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 a 2x2 table. Based on the physician-assisted data, the number of patients who need to be treated with drug X show improvement in one patient is which of the following. So what they're asking is the number needed to treat. Okay, and you always see that the number needed to treat or number needed to harm. And for our purposes, just think of them as the same thing. So number needed to treat, the formula, and this is something you just got to memorize, is 1 over the absolute risk reduction. Okay? So, but then you have to say, well, what is the absolute risk reduction? Well, the absolute risk reduction, this is like a separate formula that you really have to know. So the absolute risk reduction is the event rate of the controlled minus the event rate of treatment. So long story short, that's kind of what they are, but you got to know these formulas, okay? If you don't know the formulas, you're kind of dead in the water. But they like this question right here. They really like that number needed to treat one. So that's what this question says, number needed to treat. So they don't give us the absolute risk reduction because they would say it in the question. What they do give us is placebo versus drug. Now placebo is like a control, right? So the placebo is like the event rate of the control, and then the treatment would be actually the drug. So they say that based on the physician-assisted data. So we have two types here. We got patient-assisted, physician-assisted. So they want this one. So don't fall in the trap. We don't care about that anymore because we want the physician-assisted. So now we find the difference between the placebo or control and what the drug said. And what's the difference between 60 and 35? That's actually what? 25, right? And we don't deal with percents in math. We deal with basically decimals. So 25% is 0.25, and that's your absolute risk reduction. That's the difference between treatment and placebo, your absolute risk reduction. They usually give you a chart to make you find this. So now you take that number here and then plug it back in to our formula for number needed to treat. And so 1 over 0.25. Now I can solve that, but if you don't know how, whatever basic math tips that you've kind of learned throughout the years, sometimes you say, well, that was 25%. I know 25% is 25 out of 100. And how do I get rid of a fraction on bottom? I just do the inverse of it, so just flip it upside down. And so the bottom cancels out, and on the top, I'm left with 100 over 25. And again, that's just some basic math. If you can get to this stage, you're in shape and just solve from there. So what's 25 over 100 over 25, or 100 divided by 25? Answer is going to be 4. So in this question, they ask you what was the number needed to treat. You got to know the formula, and then you got to know this formula one extra step because the absolute risk reduction is actually a formula within itself. And then when you plug those numbers in, you're going to get answer choice A, as in 4. Okay? Very good. Next one says, basically let's go to the question. It says, which of the following is a positive likelihood ratio? Now you'll see these things called likelihood ratios, and most of us don't know what those are. We always have to look these things up. But in step 1, step 2, and even step 3, you're going to see this thing called likelihood ratio, and it's all fair game, and it's all based on the formula. So likelihood ratio, you have a positive likelihood ratio and a negative likelihood ratio. And basically likelihood ratio just says it's looking at a test and saying, really kind of how accurate is this test doing what we want it to do. But they don't really care that you know the definition. What they're going to do is they're going to give you this kind of stuff and actually say, can you figure out what the likelihood ratio is? So we got to know what the formula is. So likelihood ratio, think of it like this. Always say sensitivity over specificity. And this is for both of them. Sensitivity over specificity. Likelihood ratio only has to do with that. It really has nothing to do with these guys. So there's one extra step. The positive likelihood ratio, you're going to put a 1 minus the specificity, and the negative likelihood ratio, you're going to put 1 minus the sensitivity. Okay? So as long as you know it's sensitivity over specificity, and then the positive one has the 1 minus on the bottom, and the negative likelihood ratio has 1 minus on top, these are the formulas that you have to know. Okay? That's why these questions aren't as much fun, because it's all based on memorizing these silly formulas. So from that, we go back to the problem, and all this is just kind of smoke and mirrors up top. If we know we're looking for this, all I need is sensitivity and specificity. So then we just plug them in. They asked for the positive likelihood ratio, so now I know that is actually sensitivity over 1 minus specificity. And so when I plug those in, sensitivity is 70%, but we don't deal with percents, we deal with decimals. And then the bottom is 1 minus specificity, which is 0.9. So if I take this out a little further, I have 0.7. 1 minus 0.9 is actually 0.1. And if I divide that out, I get 7. Okay? So pretty easy. Once we get down, once we realize what we're looking for, we know the formula, and then we just kind of plug it in. Once you know the formula, just plug it in. Just kind of review your basic math skills. But they do like this likelihood ratio formula. The positive and the negative. The only difference is where you put that 1 minus, okay? Alrighty. So this one says, a prospective study was conducted to assess the relationship between elevated PSA and prostate cancer. Patients were selected at random. Results showed a 20-year relative risk 4.0 for men with elevated PSA compared to the men with normal PSA. If the p-value was 0.03, 95% times 5% confidence interval, 1.5 to 5, then what percent of prostate cancer can be attributed to elevated PSA? So whenever you see a problem on step 1 and it says what percent, anytime they're dealing with percent, the only questions that I've really seen on step 1 then when they talk about percent and make you find this is going to be the attributable risk percent, okay? And so what is that? Well, the formula for that is just relative risk minus 1 over relative risk, okay? Because it's the risk, or the attributable risk percent. Attributable risk percent. So all we need to do is a relative risk, okay? It's the relative risk, minus 1 over relative risk. So from that, all we need to do, so whenever I see percent, I jump on this formula right here, one that we have to memorize, and then I just plug and chug. So relative risk is what? Relative risk, they told us in it. Relative risk right here is 4. So I go 4 minus 1 over 4. 4 minus 1 is 3, divided by 4, and I get 3 out of 4, or 3 coins out of $1, is what? 75 or 75%. Answer choice F. So pretty basic problem. And the only thing that you really need to do is, again, it goes back to knowing the formulas. And again, none of us like to memorize these things, but we want all the points we want on step 1, so we got to do a good job. All right. This one talks about the, let me see if I can kind of zoom in a little bit. That's going to be hard. So a research group, it talks about a research group is studying a new biomarker for a disease in a random sample of asymptomatic patients greater than 70 years of age. As the majority of this type of disease is slowly progressive, that's interesting, slowly progressive, the investigators are concerned that the new test will be overestimated due to the detection of a disproportion of slowly progressive benign cases. The investigators are concerned about what type of bias. Okay, so you have all this, biases that are in the, you see them in the step 1 first aid book, all that kind of stuff. But the key with this one is, so the researchers are worried, but what they're worried about is the fact that they got all these they're finding all these diseases that are slow, benign cases. So, they're just detecting them, and these people are living and living longer, but it's mainly because they're finding, it's more about the disease being more benign cases that they're adding in there. So whenever you see that, whenever you see benign cases, if it says benign, you're going to go with length time bias, answer choice E, okay? That's just a flat out, just know it, okay? Benign, slow growing, anything like that, that's adding to why people are living longer. It's an illusion of most of them living longer. Length time bias. The one they want you to bite on, and of course we always put it answer choice A, that's how they do things, is lead time bias. Remember, lead time bias is just when you're detecting the disease earlier, okay? It's like in prostate cancer, instead of detecting people at, say, 60 years old, you're detecting them at 50. So this gives this illusion now, if we're getting them at 50 and they're living to 80, people are living longer. And it's like, well, no, that's not the case. The case is actually just finding these people a little bit earlier. That's lead time bias. Length time, more benign, slow-growing cases. So you really have to know these two. They like to test between those. Hawthorne, obviously it was people who know that they're being watched, so they change their behaviors. Sampling bias, something like where, you're doing a test and the test was on, like, say, a Hispanic population, and you're trying to say, well, does that really apply to everybody that everybody else in the world? Can I adapt those results? So, but I just want you to know length time, lead time for right now. This one says, a drug ABC versus standard therapy in preventing UTIs was recently published. A study of the drug. The absolute risk reduction, for drug ABC versus standard therapy is 6%. So I'm going to say 6% or 0.06 because we deal in decimals. If the incidence of UTIs with standard therapy is 8%, and there are 29 UTI patients in the drug ABC group, how many total subjects are in the drug ABC group. All right, so when you look at this, you say, man, I have no clue where to start. Well, what do I know? Well, I know absolute risk reduction they gave me, and I know the formula for absolute risk reduction is the event rate of the control minus the event rate of treatment. So let's just start there and see if we can figure this out. They told me the absolute risk reduction is 0.06, so I can put that right there. And then it says if the incidence of UTIs with standard therapy, okay, remember standard therapy is like your control, that's your baseline, that's your gold standard. So standard therapy is 8%, so that's the event rate of the controlled is 8% or 0.08. And there are 29 UTI patients in the drug group. So here's the drug group because this is a treatment. And usually there's some percent, but all they're giving us is the number of people that actually tested positive for it. So there's 29 people out of some number, and actually that's the question that they're asking us, is the total number of subjects in there. So here's our formula. So if you can get to this point right here, you got the battle half won. So absolute risk reduction is event rate control minus event rate treatment. So now let's solve for x, and I think we got this thing. So let's to get x by itself, we got to move everything to the other side. So 0.06 minus 0.08, well, technically that's like a negative number, and that's okay for right now. So that goes away, and all I did there was some basic math, 0.08, I'm sorry. And I get -2, and on this side I got -29x, or minus 29x. So I can get rid of the minus sign, just if, let's just say I multiply both sides by -1. I can do that. If you do something to one side, do it to the other, it goes away. Basic math. And then I'm left with 0.02 equals 29 over x. So again, solving for x, I can multiply both sides. 0.02x equals 29, and I can divide by x. Oh, what am I doing? I'm doing the same thing. I'm divided by 0.02, I'm sorry. So x equals 29 divided by 0.02. So then I take this, I say, well, can I divide 29 divided by 0.02? And I say, well, I can go 1, 2. Decimals, if I don't see it, it's at the end, 1, 2. So now I got 2 that will go into this. So 2 goes into 2 once, carry down 9. 2 goes into 9 4 times. Okay, 1, bring down to 0. 2 goes into 10 5 times. That makes it nice, and bring down to 0, and then 0. So this gives me x, and x actually went right there, so that's the number of people. So x equals 1450, and actually this should be this guy right here. It should be it's choice D, but it should be 1450 because 2, 1, 2, 4, it should be 1450. But the moral of this problem is, when you see something like this, don't get confused, don't get upset. Just ask yourself, what do I know? Well, I know a couple formulas. They told me I start out with absolute risk reduction. I know that guy. And then all I did was read the problem and plug in some numbers. And then you just got to know your basic math, how to solve for that x, and then you got it. But I want you to know this, guys. Know your formulas and know how to plug things in. Don't get frustrated. Ask yourself, what do I know? All right. This one says, you're asked to assess the efficacy of a new psych drug which is being hailed as a new blockbuster. The result of a randomized control trial at 8 years is given in the table below. Okay, treatment, new drug, placebo, psychosis, no psychosis, 2x2 table. What is the number needed to treat? Okay, so it's one of those number needed to treat ones. And we talked about this a second ago. Number needed to treat equals 1 over the absolute risk reduction. Well, what's the absolute risk reduction? Absolute risk reduction is event rate control minus event rate the treatment. So let's figure this out. Event rate controlled, the control would be placebo, so that's going to be this guy. So it's 30 people had psychosis and 970 didn't, so 30 people did out of 1,000, and all I did was add these guys up. And then minus the event rate of the treatment. Well, the treatment's a new drug, and there's 15 people that had psychosis out of, well, there's out of the whole bunch, there was 1,000 people. So that's going to be my absolute risk reduction. So what's the difference between those? Is 30 minus 15 is 15 over 1,000, just some basic math. So that's actually my absolute risk reduction. And I plug that in just like before. I have 1 over 15 over 1,000. It's nice. It's in a fraction form. It makes my life a little easier. So then to get rid of this fraction on bottom, I just got to multiply by the inverse. So flip it upside down. And whatever I do to the bottom, I got to do to the top. Bottom cancels out. And I'm left with 1,000 over 15, or 1,000 divided by 15. Now, can 15 go into 1? Nope. Can 15 go into 10? No. Can 15 go into 100? Yep. How many times? 6. That's 90. I'm left with 10. I bring down my 0. Can 15 go into 100? Yep. 6. Okay, and that's 90. And you see the pattern there. And I could put a decimal, and I keep running into this whole 6. So my number needed to treat is actually going to be 66.6, but if we're dealing in people, we got to either round up, round down, and we're going to round up, so 66 is actually going to equal 67, which is going to be answer choice E. So in this one again, what are they asking? Number needed to treat. You got to know your formula, and you got to take that and expand it all the way down to this. And from there, you just find the difference. Attributable risk reduction, absolute risk reduction, is just a difference between something. It's just a difference between them. You do that, put it over 1, put it under 1, and then just solve some basic math. So it can be done real quickly. All right, now we got Hardy-Weinberg stuff. All right, so the key with Hardy-Weinberg, and let me just kind of jump ahead because this is something kind of popular, nobody likes it, is there's 2 formulas that you got to do with Hardy-Weinberg. Whenever they're dealing with Hardy-Weinberg stuff, basically Hardy-Weinberg said, look, let's just figure out the chances of seeing stuff in a population that has, no kind of skews and stuff like that. So there's 2 formulas. First one is this p squared plus 2pq plus q squared equals 1. And this other one's p plus q equals 1. So this formula here is just the alleles and the genes. So if they talk about like if you have a gene for a certain thing, they're talking about this p plus q. Now p, you always have to know is associated with the dominant. Q is going to be the recessive, and these are just alleles. And if I add the dominant plus recessive in society, it should equal 1. You got to know it. Now, when they start talking phenotype, this is just what? Phenotype is like how things are expressed. So this goes down to p squared plus 2pq plus q is 1. So again, p is the dominant. So p squared represents the dominant expression of someone carrying both dominant alleles. And then the 2pq is actually going to be expressed what? It's going to actually express as a dominant, right? Because it has both dominant and recessive, but dominant obviously is dominant, so it's going to be expressed. So that's going to be someone that's called what? Heterozygous, right? Homozygous had both the same. Heterozygous got 1 of each. And then this q squared. This is super duper important, right there. The q squared is going to be the recessive, recessive expression. Okay. Now this is kind of how this is how they test. Okay. They're going to give you something, and pretty much they always do it this way. They give you q squared. Somewhere in the problem they give you q squared, and then from this you can work backwards and you can find out any one of these, because I can take q squared and do what with it? I could technically take q squared, take the square root, and now I got q. Well, I know if q plus p equals 1, then I can find p. And then if I know both p and q, I can solve any of these guys. So long story short, when you see Hardy-Weinberg problems and they start talking all this kind of stuff, the recessive expression in a population, just know that you're looking for q squared. Take the square root of that, work backwards, and you'll solve all these problems. So here's our problem. Hardy-Weinberg. It says 16% of the population is unable to smell a chemical bubble gas. These non-smellers are recessive for the smelling gene. What percentage of individuals in the population are smellers? All right, so this first one is just basically, if 16% of people are non-smellers, how many are smellers? Well, it's everybody else, right? So what's 100 minus 16? And you actually get 84%. So first one's not even like a Hardy-Weinberg thing, it's just some basic stuff, okay? Basic common sense. If 16% of the people can't do it, well, the remaining people can. So that would be just 100 minus that. Now, it says, what is the frequency of the dominant and recessive allele? Well, what's key is they said that 16% of people are recessive for that smelling gene. They're recessive. So what does that mean? That's recessive expression. It's not a recessive gene. It's a recessive. They're saying they can't smell, and smell is is some type of expression of that. So this 16% actually represents q squared. Okay, so that's q squared equals 16%. So remember what we said. They're going to give you the recessive. Now you just work backwards. Okay, I can take the square root of that and come up with q. What's the square root of 0.16? Just ask yourself, what times itself can give me 0.16? And if you didn't know, you can just kind of write these out until you get it correct. And the answer is going to be 0.4. Let me show you. If I have 4 times 4 is 16, 2 decimal spots, 0.16. So it's 0.4. Now, again, if q is 0.4, I know that p plus q equals 1. So q is 0.4. So I know p has to equal what? What plus 0.4 equals that? It's 0.6. So there we go. What is the frequency of the dominant allele? 0.6. What is it about the recessive allele? Well, recessive is going to be 0.4 because I work backwards. So that answers that one, 0.6 and 0.4. And then it says, what percentage of the population are heterozygous for the trait? Okay, so heterozygous. Remember heterozygous? That's 2pq. Heterozygous meaning they have one of each. Homozygous means they have both of the same. So then I just take what I know. 2 times p plus q. And then you can kind of solve that out. You know, it's, let me see, 0.6 times 2, 1.2 times 0.4 is 8, 0.48. 0.48 or 48%. Okay, some basic math. But again, the key with Hardy-Weinberg is they're going to give you the recessive expression, which is basically q squared. And then from there, you take the square root of it, work backwards, find q, then you find p, and then you can solve anything that's in those equations. But you must know the equations, right? You must know the equations. All right. And we already talked about that one. All right. So looking at this one, this is just another Hardy-Weinberg problem. You know, healthy 25-year-old, she comes in, she has a kid. She desires to have another kid, but her actual husband has a little problem, so he can't do it. So she went out and, you know, had a sperm donor or whatever, but then she comes out and her kid has some rare autosomal recessive disease. Okay, so and this disease is known to affect 1 in 90,000 people. What is the probability of the patient who would have a second child affected with the new healthy sperm donor? So kind of a complicated problem, but we knew right off the bat, they started talking rare autosomal recessive disease, and they gave us some ratio of the frequency of this rare autosomal disease. So I know they're talking Hardy-Weinberg. So what are my two formulas? Okay, p squared plus 2pq plus q squared equals 1, and then p plus q equals 1. This is the phenotype expression, this is the alleles, okay? And they always give me this guy, which they did. They said that's 1 in 90,000, and that's q squared, okay? That's the expression out there in public. All right, so how do I work this? I could say, well, basically what's the question? It says, what is the probability that the patient would have a second child affected with new sperm donor? So this gets into a little bit of genetics, but well, we know the mom, you know, she has this gene, okay? So chances are, you know, if we're drawing one of those, you know, Punnett square deals, you know, mom has this, and then she's got the gene down here. So chances are she might give this as to her offspring is going to be 1/2, okay, 1/2. Now the chances of her finding another person, you know, with a new healthy sperm donor, well, this healthy sperm donor is drawn from the public, and that's what Hardy-Weinberg says. He's just giving ratios in the public. So we're looking to see what is the gene frequency, the allele frequency of someone random in public. So now we're dealing with this guy over here. So we're not really looking for you know, the q, because that's the expression. We want to know the gene. So we take the square root of that, and then q equals 1, and what times itself gives me 90,000, and that's going to be 300. So, you know, a guy off the street per se, his would be 1 in 300. So if we combine the guy off the street with the 1 in 300, which is basically q, with the chances of it coming from mom, well, we already know she's got it, so it's a 1 in 2. So her plus this guy is going to give me, we multiply across the board, 1 times 1 is 1, 2 times 300 is 600. So what is the probability? 1 in 600. This, you know, this is a Hardy-Weinberg problem that was taking one extra step. You know, they gave us the autosomal recessive, and they could have asked us any of these things. They could have asked us any of them. But they went ahead and just started talking about, you know, what is it, when the woman has something with the man, what's the ratio? But if you can set this problem up and know that Hardy-Weinberg asked this, and you start taking the square root and working backwards, you can basically solve anything. So this is an interesting problem because it made you go one extra step. Most people fall in the trap of just stopping right here in 1 in 300, but the actual answer would be 1 in 600 because we're talking her genes plus his genes. What's the frequency? Okay. Let me see. This is that one. I'm not gonna worry about too much of this, so the video will be way too long. So, basically, here's a formula. When you walk into step 1, you're gonna get a laminated sheet, and that laminated sheet you can do anything you want with this. So usually before the test starts, I just write down some basic formulas and stuff. You know, and basically it's only in biostatistics. You know, this is just one area where we need to kind of really dominate, and it's really not that bad. Of an area. So here's just some formulas, and probably what I would do right when I first get in that test, I would probably go in there, and if I didn't have these memorized, I'd say, oh, well, I remember, let me see, this is reality on top, the test goes on the side, sensitivity went this way, specificity, positive predictive value, negative predictive value. And so those are all my formulas, and watch that first video to understand that. I'd also kind of redirect myself to say, remember, this is that null hypothesis table, and again, reality, test, alpha, beta, yeah, this is type 1 error, this is a type 2 error, and then 1 minus beta is power. And you know, this is the null hypothesis, and there's no association. This one says there is an association. And remember, they like to test you on this box here, and then where you might have to actually, and they put this into words. Okay, we have to know what I'd probably write down. There's case control and there's cohort studies. Those are our two big ones. Case control is associated with odds ratio, which is one number over one number, and then we have cohort. Remember, these things look the same, so it's associated with relative risk, which is one number over 2. Okay, so I'd usually just quickly write that down, and then I'd probably come in there and say, oh, my number needed to treat or harm, think of it that way, is 1 over the absolute risk reduction. Absolute risk reduction is event rate control minus event rate treatment. I'd probably have that one on there, and then, you know, obviously the likelihood ratios, positive and negative likelihood ratios, and you can remember it's sensitivity over specificity, sensitivity over specificity, and it's all where you put the 1. And on the positive likelihood ratio, it's 1 minus specificity. Negative likelihood ratio, 1 minus the sensitivity. And so that's pretty much it. So I'd immediately kind of go in there and what else we did? We did attributable risk percent. Anytime you see a percent, you think this formula, relative risk minus 1 over relative risk. If you go in there with these formulas, guys, you should pretty much dominate the biostatistics portion of the USMLE. You know, you always hear about people maybe not passing by 1 or 2 points, don't make it on this topic. So kind of look at these, and hopefully you'll do well in the test, guys. Good luck.